Hello everyone, hope you are doing well. My name is Akash and welcome to our channel Coding Turtle. So in this video we will learn what is WebAssembly, how can we get started with WebAssembly using assembly script, and in the end we are going to implement a demo where we will sort pixels of an image and we will compare the speed of WebAssembly and JavaScript and see if WebAssembly is really better than JavaScript or not in terms of computation efficiency. So sit back, relax and watch till the very end. So WebAssembly was first announced in 2015. So it is actually an assembly-like language with compact binary format which gives you native-like performance on your web browser. So basically you can use C, C++, Rust, assembly script and many more languages to create that binary format. So with WASM, you can imagine building a Photoshop tool on web that might be possible with WebAssembly only. And you must be amazed to know that Figma is using this tool to render it images. So this was a little intro of WebAssembly. So developers, I think you should get your editor out and let's jump right into the code. So let us create a assembly script project, and to create that, first of all, we will create a empty directory. And yeah, now we have created it, and so we will creating a JavaScript project. So let us create a package.json file. So what -y is going to do, it is going to create a package.json file with the default values. So yeah, it is created. Now let us go ahead and install our assembly script compiler. So assembly script compiler is installed. So now assembly script compiler now provides you some scaffolding utilities which provides you some directories and some files which help you in getting started very quickly. So let's go ahead and install them. So npx asinit dot this command is going to give you that scaffolding files and directories. So as you can see, it is installed currently, and we'll go through them one by one. What has been installed, what has been done for us by the assembly script compiler. So this is the demo project that we created right now for our WebAssembly. So as you can see, these are some of the directories that have been created by WebAssembly. So let's go through them one by one. In the assembly directory, you can see there is an index.ts file, and if you open it, then you can see there is an add function that has been created. It is a simple add function which takes two parameters, type integer 32 and returns out integer 32 only. So this is created by default, and you can create all your assembly script functions and methods inside this file, and also you can create new files inside assembly folder and you can import it and then you can use it. And if you go ahead, you can see there is a tsconfig.json file also. So this file can also be found in a TypeScript project where you tell your compiler how you want your TypeScript files to be compiled. So it is similar to that. So now let's go ahead and talk about a build folder. So actually whatever assembly script code that you are going to write in your assembly folder, it is going to be compiled and transpiled into your .wasm file, which will go into your build folder. So let us see how we can do that. So if you go inside your package.json file, you can see there's an as build script already been created for you by your assembly script compiler. So let's go ahead and run it. Yeah, so as you can see, inside your build folder several files have been created. So in this build folder you can see that there is release.js file, and there is debug.js, there is debug.wasm file, release.wasm files. So these files have been created. So if we go through the release file which are related to actually production use, so you can see there is a release.wat file. It is basically a WebAssembly text format which is like an intermediate, and it will be converted into a WebAssembly file. Now if you go to the release.js file, you can see that your release.wasm file, it has been imported using in WebAssembly API, compile stream API, and your return method that you wrote in your assembly script, it is been exported here, which you can use in your JavaScript application. So we are going to use this, and if this seems intimidating at first, then you don't need to worry about it, and we will look into it and we'll compile our WASM file using WebAssembly APIs. So now if we move ahead, then there's a node modules folder which is as usual present in every JS project. Now if you go to the second folder, there is a test folder, and you can write your test cases for all the assembly script methods that you have written. So like there is an add method test case written here, so you can write it and you can run the test cases using command npm run test, which has already been provided in your package.json file. So you can see there's a test command already built, so you can use that. So let us now go ahead and review our asconfig.json file. So in this file, actually this file is a compiler options for your assembly script. So whatever options you are going to give here, your WebAssembly file is going to compile according to that. So let's see, there's a targets key, then there's a inside that there's a debug key and release key. So debug is for development and release is for production use. So basically there's a output file, what type of output file you want to generate. Of course we want a WASM, so we are going it with the WASM, and it will be generated inside the build folder. And there's a W80 file which is generated, which is kind of a readable format, intermediate format. So this is also generated inside the build folder. So now if we look in our release production for now, release key, so we can see there's a source map. Map has been set to true. So what source map does, like it is a mapping which is generated for your original code and your final code. So actually it helps to when you want to debug your WebAssembly code on your Chrome browser or any other browsers. So if you go inside the build folder, you can see there's a .map file generated. There's a release wasm.map file, and there's a debug wasm.map file. So this is the mapping. And now if we go ahead and check, there's an optimized level key. Optimized level is set from 0 to 3. So 0 being you are asking the compiler to optimize it minimally, and 3 being asking it to optimize as maximum as possible. Now if you go to the shrink level, then it takes value from 0 to 2, 0 being the smallest size and 2 being the largest size. So of course we are telling here our compiler that you optimize it to the maximum level and you shrink it to the minimum size as possible. So these are some of the options that we can see. So there are multiple compiler options that you can pass to suit the compiler needs according to your. So currently you're looking at the documentation of the assembly script book for the compiler options. So if you scroll down, then you can see that most of the features are actually standardized by WebAssembly, but there are still some of the features which you can enable or disable according to your needs. So if you go through some of the flags, then there is an import memory flag. So if you're going to pass this, then a memory object will be exported which you can use to access the buffer of your WebAssembly. Then there's a no export memory, then it is going to stop exporting the memory and you won't be allowed to access the memory buffer of your WebAssembly. Then there's an initial memory flag. So basically in WebAssembly there is memory is set in pages, and in every page there is 64 kilobytes of memory. So suppose if you want to allocate 64 KB of memory, then you need to give one page of memory to your WebAssembly. So this is what we are going to set in the initial memory. And in maximum memory, what is the maximum number of pages that you are going to use? Suppose there's a need of 128 kilobytes memory that your program will be using. So you need to set maximum memory to 2 pages. So these are some of the flags that you can use. Then there is one more important flag that I would like to talk about. There is export runtime. So in WebAssembly, there are certain personal methods like underscore new, then there's underscore collect method. So these methods allows you to play with the memory directly, which JavaScript doesn't give. So if you set this export runtime true, then this method will be exported and you will be able to use these methods. So now we have one final file left, which is index.html, that we need to talk about. So as you can see, we have imported our add method that we wrote in our assembly script, which we wrote here, and actually it was boilerplate which was given to us. So it is exported from a build release.js file. So if we look at the release.js file, you can see that we have imported the release.wasm file and we have exported this add method. So this is what we are using here. So as you can see, we have added 1 and 2 number, and so let's try this and run it. So we can run it using npx ser. Let's go ahead. So you can see this numbers are added. So this was our first add method, which was written in assembly script compiled to WebAssembly, which we are running in our web browser. So let us now go ahead and write some assembly script code on our own. So that will give us some more confidence here. So let's go inside the index.ts file. Let's remove this demo code. So what we are going to do is we are going to build two methods. One will be randomizing the array. We will generate our array with random values, and second method will be generating a sum of all the numbers present in that particular array. So let's first build that randomizing the array method. So we are going to name it randomize array. So it is going to take one value which will be total length. So what length of the array you want to generate, and it is going to return the array type, your array. So let's create the array here in 32 type array, and this is the total length of the array. So whatever we pass 10, 100, 1000, that length of the array will be generated here. Now we are going to loop through this array, and we are going to fill each value with some random values. So let's loop through it. So let's set the values. So we want it to be of integer 32 type. So we will going to use math.random function, and we will use total length. So what happens here is math.random returns a number from 0 to 1 being the exclusive number. So whenever you multiply it by total length, so the number will be generated from 0 to total length, and total length being the exclusive number. So this way we are going to set all the random values, and now we are going to return this. Now let us build the second method, which is going to sum all the values in our random array. So we are going to name this method sum, and it is going to take input array which will be of type int32. So, and it is going to return unsigned 64-bit value. So why unsigned 64-bit? That because this array can be of when we are going to sum through this array, and that value can be of a large number. So that's why we are going for U64. So let's create a random value, simple variable. It will be set as 0. Now let's loop through this array. So we are going to just a simple function. We are going to sum, and we are going to return this value. So in WebAssembly, as you can see, we are using different types, like there's int32 array we use, there's i32. There are also multiple types here. So there's i16, there's float values that you can use. So according to your needs, you have to figure out what type that you need to use here. So we have written both the methods, randomize array and sum, in our assembly script. So now we can create a build and convert this assembly script methods into a WebAssembly. So let's go ahead and create the build. npm run is build. So this command is going to create a .wasm file for both release and debug. So as you now we see in our build folder, if you go to release.js file, as you can see, both the methods are being exported. So let's use these methods in our index.html file. So we are going to remove this boilerplate code, and we are going to export and import this methods, randomize array and sum, and let's so we are going to sum the array that randomize array is going to return. We are going to sum all the values. So randomize array takes one input, which is total length, and let's create a array, random array of 1000. So let's now run the server. We can run the server using npx serve. So let's proceed. So our server is running now at port 3000. So let us now and go to the browser and check it. So localhost 3000. So we can see there is an uncaught type error where it is saying that _new is not a function. So why is it so? Let's go to our build directory. So in our build directory, if you go to release.js file, so we can see there is exports._new method which is being used. So what happens is in WebAssembly domain there is a memory buffer which you can access through your JavaScript app. Okay, so this underscore new method, it allows you to allocate some memory in your WebAssembly memory buffer. So but to use this, there is clearly mentioned in our this but to use this, it is clearly mentioned in our assembly script compiler options that you need to enable a flag. So let's go ahead and check the documentation. So if we see the documentation in the compiler options, you can see there's a flag export runtime. You need to enable this flag to use this underscore new and underscore collect methods. These methods allow you to underscore new method allows to allocate some memory, underscore collect allows to garbage collect some memory. So let's go ahead and enable this flag. So if we go to asconfig.json file, this is our compiler options file. So let's enable the flag export runtime. Let's set it to true, and now we have to create the build again. So let's create the build in as build. So new build is being created. Okay, so now we can run the server. Let's run the server now. Yes, now let's go ahead and check in the browser. So if we reload the app, yeah, as you can see, we are getting the output now. So it is unsigned 64-bit number. So we ran our first assembly script program and we are successfully able to sum the array. So till now we have created two methods in WebAssembly, randomize array and sum method. So how about we create the same methods in JavaScript and we compare both the speeds and check if WebAssembly is really fast or not. So let's just create the clone methods in WebAssembly. We are just going to use those methods that we have written, and only thing we have to do to convert them in JavaScript is remove the types. Since we have removed the types, and let's name them sum.js and randomize array.js. So these are JS clone methods, simple methods. So now let's create two buttons, and one will run JS script methods and another will run WebAssembly methods. So two buttons are created now, so we can attach the event listener to them. So let's attach them. So click event listener. Same we will do for WebAssembly. Just we are going to change the ID WebAssembly. So now what we are going to do is we are going to check the time when the script execution start. So for that we are using performance.now. You can use new date also, but performance.now is much more accurate. So let's do that. And one more thing, in randomize array, since randomize array accepts the total length, why not save a common variable which we will use? So let's say we will use a length of 1000 for both WebAssembly and JS. So let's store our answer in a variable named ans, and let's sum the values, randomize. So it is sum.js method actually, so we are going to use sum.js, then randomize array.js, and in randomize array.js we are going to pass the total length variable. So now we are going to again track the time when the script execution ends. So we are going to use the same method performance.now. So since this will be a synchronous method, so script will stop here and compiler will not go on the next script until this execution is completed. So we will get the current T2 and T1 time. So now let's create a console.log or time difference. So this will give how much time it really took for the script to execute. And the same thing we have to do for WebAssembly also. Only thing is we have to remove the JS, and these are the imported methods from our WebAssembly module, and this will give us the right answer, and just label it that this is a JS console and this is a WebSM console. So yeah, this looks good and we can go ahead and run it now. So I've reloaded, and as you can see we have two methods. Let's run JavaScript first. So we have actually two methods. So let's run JavaScript first. So as you can see it took 0.7 time, and now let us run WebAssembly. So 0.5 time. So since it is, we are currently using 1000 length array, so how about we increase the array and see the limit. So I am going to increase 3 more zeros, so it will 10 to the power 6. So let's go and execute it. I have reloaded the app. Let's run JavaScript. So it is 39.1 and WebAssembly 20.5. So we can see some differences here, guys. And let's increase 2 more zeros and see. I'm going to increase 1 more zero actually. Let us see what the difference it makes. So JavaScript 158.6 for JavaScript, and for WebAssembly 108. So it is clearly visible that even this simple methods WebAssembly is beating JavaScript. So let us jump to more complex example and check if WebAssembly is really better than JavaScript or not. So this is our second app that we are going to build in WebAssembly. So as you can see, this is a final demo. So what we are going to do is we are going to generate a image of random pixels, and then we are going to sort that pixels based on their luminous intensity. So we can choose the compiler which script to run. We have just like we did in some example, we wrote the same methods in JavaScript as well as in WebAssembly. So we have done the same case in this app also. So like for example, I choose the WASM compiler, and then if I run the generate and sort method, so as you can see, yeah, a random pixel image is generated. This is just random, and the time taken to generate and sort these pixels, as you can see, it is sorted based on their luminous intensity. And now again, if I click it, and as I click it, a random image generates, and it gets sorted. So if I now change the compiler to JavaScript, now if I click, so as you can see, it is still doing the same job, but the time taken is much higher. So let us go ahead and implement this. So let's go ahead and create a basic HTML first for our app. So I'm going to wrap my content inside a div and center align all the items using basic styling. So currently I'm using inline styling, not using any external file since it is a demo app. So let's go ahead, align item center and justify content center. Okay, so this is done. Now all the items will be centered. Now let's create a heading. So it is sort image pixels, and let's create a button now which will generate and sort our pixels. So this is a button. Let's give it an ID, sort button. So yeah, that is done. Now we need to display time also. So let's give an heading so that we can display time. Its ID will be time taken. So it is time taken. Okay, so this is done now. Let me scroll down so that you can see. Now we have to create an input drop down menu so that we can change our compiler. So first create a label for now. So choose a compiler. Now we have to create a select input, and we are going to give the options here. So let's give it some margin also so that there is some readable space out there. So let's give 0.5 em of margin. top, and let's give it an ID of wasm-js for now, and let's set the option. So there will be two type of compiler actually. One will be of WASM type, another will be of JavaScript code. So let's give them this JavaScript, and another option will be, one will be WASM, another will be JavaScript. So these two drop down menu is ready so that we can change our compilers and run the code according to that. Now we have to create two canvas. So in one canvas we will generate a random image and create random pixels, and in the another canvas we are going to sort that pixels. So let's go ahead and create this. So first canvas, let's create a clone for that. So first canvas, let's give it an ID. So just it is a simple canvas in which we are going to generate random pixels, and in the another canvas it is the sorted pixels. So let's give it sort canvas ID. So ID is given. Let's give them some basic styling now. So in terms of basic styling, let's give them some margin top so we can clearly see in the UI. So let's give it 2em for now, and background color will be black. So this is done. Let's copy the same style for another also. So yeah, so our basic HTML is ready. Now let's go ahead and run the server and see if our UI is showing fine or not. So let's run the server and let's run it. So it doesn't look good, and it seems like the items are arranging in the row pattern. So what we need to do here is we need to just change the flex direction. So flex direction will be column, because for display flex it is by default row. So let's go ahead and run it now. Reload that. Yeah, so it is showing fine as you can see. So let's go ahead and now run our JavaScript and write some JavaScript there. So let us now create an index.js file in which we are going to write our JavaScript, and let us load this file in our HTML. So it should be script, and source will be index.js. So we will going to default the script because we need our HTML to load and parse first. So let's go ahead and write it. So in our index.js file, we are going to first get our canvas. So we have created two canvas here. So what is image canvas and sort canvas? Let's use them. So document.getElementById. One is image canvas, and similarly another canvas is sort canvas. So let's name it sort_canvas, and its ID is sort_canvas, sort-canvas. Now let's go ahead and create the canvas context. So by creating the context for the canvas, we can actually make any changes. We can update the pixels inside the canvas. So we need the context for that. So let's go ahead and create the context. For this canvas, we are going to name it CTX, and we are just going to name canvas.getContext. So it will be 2D context, and let's create another context that is for sort canvas, and it will be sort_CTX, and it will be sort canvas. So we have created them. So let us now attach the event to this sort button, because whatever we want to do is when this button is been clicked, we want to create the image and then we want to sort the pixels. Okay, so let's attach an click event to get element by ID. So it is sort_button. So we are going to attach the event, which is a click event, and so yeah, this method is going to execute when this button is being clicked. Now we need to take the input, what type of code we want to run. Like I told earlier that we are going to create same methods for JavaScript as well as for WebAssembly. So user can decide whether he wants to run on JavaScript or WebAssembly. So we need to check what is the compiler that user has chosen. So let's get the ID wasm-js, and we can get the value here. So we can name it constant run_on, So we can get the id, get element by id we have copied, and its value. So either it will be WASM or JS. As you can see, it is WASM or JS. So according to that, we are going to run our code. So we can just create a simple if here and run on. If it is WASM, then run WASM code here. Else you have to run JavaScript code. So first we will going to make some JavaScript code, and then we will jump to WebAssembly code. So first of all, we will decide what width and height of the canvas we want to create. So for now, let's keep it to 500, width 500 and height 500. Okay, so these two are created. So let us now give width and height to our canvas. So it is canvas.width, canvas.height equal to h, and same we are going to do for our sort canvas, since we created two canvases. So it is sort canvas. So we have given this width and height. Now what we have to do is we have to create a random image. So let us create a method which will create a random image. Function generate random. Okay, and we are going to take this in. This function is going to return random image pixels, and let's store it in random image variable, and let's call it generate random. And since we are generating a random image, then we need to decide what width and height we need to give, or what width and height of image we need to generate. So since we have already decided it will be w and h, so let's pass this variables w and h, and let's receive them as arguments also. Okay, so now let's focus on creating a random image. Okay, so to create a random image, we can use image data class. So image data class, as we talk about, it is it contains all the underlying pixel information which is inside a canvas. So constructor of image data accepts two parameters, which is the width and height of image that we want to generate. Now we store the random image data. So random image data will be, we are going to get it from rand image dot data. So this rand image dot data actually consists of all the pixels that is in your image, and it is represented actually in one-dimensional form. So to give you an example, suppose this is an image of 3 by 3 pixels. Okay, and each pixel will consist of all the constituent colors like RGBA. Every pixel is formed using these colors RGBA: red, green, blue, and alpha. Alpha is the opacity of your color, and these are 8 bits in integers, so they take value from 0 to 255. So suppose you have an image of 3 by 3 pixel, then your random image data, which is all your pixels in one dimensional form, so it will be represented something like that, RGBA. So this is 1 pixel, but these are all 8-bit values. Then again for second pixel it will be RGBA. So this array length will be around, for a 3 by 3 pixel image, it will be around of 9 into 4, which is 36. So this is the array length that will be for this random image data. Now if we have given width and height as w and h, then it will, for w and h, its length will be w into h into 4, because each pixel is represented by 4 values. And since they are 8-bit values, so this array would, if you print this array, this would look something like 127, 253. So each value will be, each pixel value will be between 0 to 255. Okay, so let's go ahead with the implementation now. So what we have to do is we have to create this pixel as random values. Okay, so we are going to generate random pixels. So let's go ahead. For every pixel we have to generate random RGBA values. Okay, so this is what we are doing right now. So let's go ahead and do that. So let me just remove it. So let y equal to 0, y will be less than h, which is our height, and y plus plus. Then we will let x equal to 0, x less than w, x plus plus, and w is our width. Okay, so we are going to loop over this. Now since we are traversing through all the pixels on x-axis and y-axis, so since the pixels are in a two-dimensional form, but it's our random image data, it is a one-dimensional array. It is a 1D array, so we need to map this 2D array to this 1D array. So if we want a pixel value, suppose there is a pixel at 2, 3 position. Okay, so if we want to map this on a 1D array, what will be the index on a 1D array, then we need to apply some mapping. So how can we apply that mapping? Let's see. So suppose if you see, I have given the coordinates here. So this is a small screen you have of 3 by 3 pixel. Okay, so now what we want is we want to generate a single dimensional array for this 2D array. Okay, so if you want to know what will be the pixel index, what will the index of this element when it will be mapped to a 1D array. So what you can do is you can take how many this is row and this is column, so you can multiply row by total width, which will be 2 into 3, 6 plus number of columns that have passed. So this is going to give you the pixel index. So for example, if I want to generate pixel index, then what I can do is I can just multiply my row with my width, then I can just add x. And now since they are, as we discussed, there are four values for every pixel RGBA, so we need to multiply by 4. So this way we get the pixel index. Now once we have the pixel index, now we can start writing the random values. Okay, so let's write the random values first. So random, we are going to, since this is our 1D array and inside this we are writing the random values. So let's do it. It will be mat.floor. Since every RGB is an 8-bit integer which takes a value from 0 to 255. Okay, so we have to generate a random value between 0 to 255. So this is going to give us a value from 0 to 255. Okay, and to remember this is a red. This is generated for red for 1 pixel. Now similarly we have to do for green, and it will be index +1. Then we have to do for blue. Okay, and then we have to do for alpha. Okay, so this is for green, this is for blue, and this is for alpha. For alpha is actually the opacity of your color, and since we want our maximum opacity, so we will hard code it to 255 for now. Okay, so it will be hard coded to 255. So it looks good right now that we have generated the random pixels and for every pixel value. So let's go ahead and return our random image data now. Okay, so we are going to get this inside our random image. Now what we can do is, once we have a random image, we have to write this image data to our canvas. So since our default canvas was this canvas and its context was CTX. Okay, so we have to just put the image data to our canvas context. So how can we do that? So there is a put image data function which is possible, which allows us to write the image data to a canvas context. So it is ctx.put image data, and our image data is random image. Okay, since this is what we generated here, so it will be random image, and then we have to give the pixels coordinates from where we want to write. So it is 0, 0, so that is written. Okay, so this is done, and this will be generating a random pixel for now. Okay, So let's go ahead and see. So as you can see, we are going to generate for JavaScript right now. Let's click on generate and sort. Yeah, so our amazing image with random pixels is generated here. We are filling random values here, and this looks good to us. And now what we have to do is we are going to sort these pixels according to their luminous intensity, and we are going to discuss what is the luminous intensity. Okay, so let's do that now. So we have generated our random image now. So this random image pixel data that we have generated, let's console this and see what is actually inside this. Let us print its data value. We have consoled it, and let's go to the image. I have reloaded, check the compiler to JavaScript, and generate and sort. So yeah, we can see our data pixel array. So let's scroll it a bit. So as you can see, yeah, so these are actually pixel values. So starting for 0, this is the first pixel. Okay, RGBA, and as you remember, we have hard coded our alpha value to 255, and this is second pixel RGBA, this is third, so on, it goes on for every pixel. Okay, so what we are going to do now, this is the random pixel generated, and we have to sort this array. Now it is a problem of sorting, so we need to write a method to sort this one-dimensional array. Okay, so let's do this now. So it is going to be sorting. Sorting is going to take an array and width and height if we need it. Let's remove this console, and we are going to call this sorting method here, and we are going to pass random image dot data, because since this is our array in which our pixels are containing, and then width and height we are going to. So this is going to sort our data pixel array. Okay, so now consider this problem is a one-dimensional problem, and we are going to opt for, since there are multiple sorting algorithms, but we are going to take a bubble sort, because bubble sort time complexity is very large, and we want to throw a more computation algorithm which is more heavy computation, so that we can really test out our algorithms. So we are going to write this bubble sort in JavaScript as well as a WebAssembly. So let's go ahead and write our bubble sort algorithm. So let's run the algorithm. So it will be let y equal to 0, y less than h, y plus plus, y plus plus, or let x equal to 0, x less than w, x plus plus. Okay, so we are going to traverse every pixel, and since you must be knowing, or if you don't, then bubble sort, you should look out in the bubble sort algorithm, that what we do, that if there's an array of random values, then we compare every value with every other value, and if we try to bring the smaller values on smaller indexes. So suppose if I compare 5 and 4, and since 5 is greater than 4, then in our next step, what we'll do is we are going to swap these values. So this is what happens for each and every value, and we keep swapping until we have found the sorted array. So this is what we are going to do this for these pixels. But one thing that will make a difference here is, since our array, it is consisting of pixels, so and every pixel is consisting of RGBA. Okay, so suppose this is R1, G1, B1, and alpha 1. Okay, and similarly there is another R2, G2, B2, and A2. So when we are going to swap these pixels, we will swap all the 4 pixels. Okay, so this 4 pixel will be swapped to this 1 pixel. But first we need to identify if this pixel is smaller than or greater than this pixel. So we need to generate a personal algorithm or some another methods that we can use to identify or to compare these pixel values. So how can we do that? So one thing is, actually there are multiple methods. So one we are going to use is brightness. So luminous intensity of a pixel, how luminous a pixel is, and based on that we are going to generate our compare our pixels. Okay, so let's name this function as brightness. Okay, so I am using this brightness intensity method, but you can use another methods also. There are multiple comparison factors that you can use to compare your pixels. Okay, so this will take x, y, and width. Okay, so we are going to use this brightness method to check actually the real magnitude of a pixel. So what we are going to do is we are going to get the pixel intensity or luminous intensity, whatever you say, intensity of brightness, and brightness will take the array and x and y and width. Okay, so this is what it is going to take, and this is will be pixel intensity 1. Since we are comparing two pixels, so it will be pixel 1 and pixel 2. So there will be pixel A and pixel B, and it will be at x plus 1 position. Okay, so now we have to compare now what from brightness function we are going to get a simple magnitude value of a particular pixel. Okay, and we are going to compare these pixels like a simple value, and if pixel A is smaller than pixel B, then it is fine. But if pixel B is smaller, then we are going to swap those pixels. So we will check if pixel intensity A and pixel intensity B exist, and if they exist and pixel intensity A is less than pixel intensity B, then let's swap it. Okay, let's swap it. And for swapping also we cannot swap simply, because we need to swap four values actually, RGBA, for one pixel. Okay, so we need to generate another method which is swap pixels, and it is also going to take array x and y and width, and it will going to swap our pixels. So what we will do is, if this is so, we are going to swap our pixels. We're going to pass array x, y, and our width. So let's now complete our brightness on swap pixel method, since they are empty for now. So first write our brightness method. Okay, so like we generated a pixel index with x and y in our previous generate random method, we are going to do that same. We have learned it that for an x and y on a 2D array, how can we map it to a 1D array? So this is what we are going to do. We are going to do the same thing. So pixel index now will be same as y into width plus x, y into width plus x into 4. Okay, so this is our pixel index. Okay, and now we have to generate a luminous intensity. What will be the magnitude of the pixel? Okay, so first thing we need to check is if pixel index is going greater than equal to array dot length, then we have to return 0 for our safety measures. We did this, and now let us create the intensity. So this is one of the formula that I got it from our Stack Overflow. It's a simple method. So you can choose other formulas also. You can learn how can you calculate more and better intensity. So the better intensity algorithm you use, the better sorting image you will generate. So I'm using a simple sorting algorithm. So it is 0.2126 into R. So pixel red pixel value, this is we are going to multiply it with 0.2126. Then we are going to add 0.7152 into pixel index of green, pixel and underscore index plus 1. Okay, and then we are going to add 0.0722 into array of pixel index plus 2. So this is for blue. Okay, so since alpha is constant 255, so it isn't going to make any difference. So let's remove that. since it is width, so I didn't use that. Okay, so this, as we see, it is going to return pixel intensity of a particular pixel using RGB for that value. Okay, so this is the brightness. Now it is going to return this and we can compare it. Now let's swap our pixels. Okay, for swapping the pixels, now we have to swap two pixels. One is at x comma y position, another will be at x plus y position. Okay, and y is constant. So let's first create the main pixel index for both the values, for both the pixels. So it will be pixel index 1. So pixel index 1, we know how to generate the pixel index. Y into width plus x and multiply by 4. Okay, multiply by 4. Similarly, we are going to do this for x plus 1. Okay, x plus 1, and it will be pixel index of second pixel. Okay, so we have generated the pixel index for second pixel. Now we have to swap the pixel values. Okay, so since there are three RGBA 4 pixel values, so we have to swap only 3 RGB, because we know that alpha is always constant, it is 255, so don't need to swap that. So we are going to run 3 loop till 2. So let's swap the pixels now. It will be array of I plus I1 plus I, and sorry, it will be pixel index of this one plus I. Then we are going to copy the pixel index I plus I equal to array of pixel index 2 plus I, and then array of pixel index 2 plus I equal to temp. Okay, so since it is not required, but still we will set the pixel index values to 255. So these are alpha values, so this will be plus 3 and this will be plus 3. So as you can see, we are swapping for every index. First we will swap the R. When I will be 0, it will be for R pixel red, inside the pixel red value. Then for when I will be 1, it will be for G, we will be swapping then B. Okay, so in this simple way we are going to swap all the 4 values. Okay, so we have applied the sorting now. So it is going to sort our pixels, and once the pixels are sorted, we are going to write the same image data to a sorted canvas context. So our sorted image context canvas context was sort underscore ctx, and we have to do the similar method, put image data. And since we have sorted the pixel inside this data, so we can write this random image and from 0, 0. Okay, so this is going to draw our pixels. And yeah, one thing that we have missed here is we are using width, but we have defined as w. So let's do this as w. Okay, so it looks good. Let's go ahead and run it now. Okay, let me open the console if some problematic comes up. So we are going to use JavaScript, generate and sort, random pixel is generated. Yeah, so we see that our pixels are not being sorted, right? There is some problem. It is not sorting completely. It is doing the sorting, but it is not sorting completely, because we need to check again and again and see if there are pixels to be sorted. So what we can do is, suppose we can add a flag did changes false, and we can apply do while loop on bubble sort algorithm, and we are going to copy this inside. So when we are swapping of pixels, we know that their pixels need to be worked on, है ना? So what we can do is we can let did changes. We did some changes and we apply this as true. And when the algorithm start, we can set it as false, that no changes has been done. So it will be false when no pixels are been swapped. But whenever a pixel is been swapped, then we will change the intensity did changes flag to true, so that we can keep going with the algorithm. Okay, so let us see if it works or not. So changing the compiler to JavaScript, running generate and sort. So it is taking too much time and it feels stuck. So our loop is kind of getting hanged somewhere. So let us see what is happening. One thing we can find here is it is x plus 1. We have passed x plus 1 in the brightness, and when x plus 1 comes here and we try to access a value beyond the width, suppose x was at w minus 1, and we try to access that value, then it might be trying to access a memory which is not accessible, or which may be undefined. So it may be swiping some undefined values. So we need to apply a check for x plus 1. So if x plus 1 is less than double width, so we can return null. Okay, so if x plus 1 is less than width, then only we will check for brightness, otherwise we will set as null, and then we will go ahead with the swapping. So let's go ahead and run it. I'm going to reload the page since it is. I'm going to, let's run it. So I'm going to change the compiler now to JavaScript again, and let's run generate and sort. So yeah, this is a beautiful image. There's a random image here, and we have successfully generated, and this thing worked for us. Our setting, this was creating an issue for x plus 1. We need to check if it is expanding the width parameter or not. So that was the case, and we can see for JavaScript we have generated a random pixel, and we are able to sort out those pixels. Now what we are going to do is we are going to generate and clone of this method for WebAssembly, and we are going to write an assembly script methods. So let's go ahead and do that. So first we'll need to write a method to import our WASM file. So earlier what we do in our earlier sum and randomized array example, we saw that we were importing the script of type module inside our index.html, but this time we are going to do it inside a JavaScript file. So to do that, there are some changes that is required. So let's see how we can import. So when we create a build from our index.ts, suppose we have written some methods here, and when we create a build, we know that inside the build folder there is a release.wasm file created that is for production use. We are going to actually import that. So let's create a method async function load wasm. So it is going to take the wasm module URL, so which will be your build release.js, and it is going to take an import object. Import, I'm going to tell you what import object does. So it is going to take import object, and we are, as the script loads, we are going to use an ify to load this script. Okay, ify will help us to execute this, and we are going to name it as async, and we will load the script here. So it will be wasm module, and wasm module will return our instances and all the exports. So we are going to use the await load wasm, and it will be build slash release.js. Okay, so looks good for now. We are going to use this. Now write our load wasm method. Okay, so since we are not passing the import object, we are going to create one. We will check if import object is not created. We are going to create one. So when importing the module wasm module, our WASM library assembly script actually accepts an import object, and inside the import object it accepts some key values and methods that is very necessary. Otherwise, we won't be able to import it. So so actually it expects env key, and env key should have an abort method and a seed method. So it can call the program whenever there is an error. Okay, and abort method will have some params that is going to pass, which is msg file line on which the error is coming in the column. Okay, so this is just going to console error the messages. So this is console error, and inside of seed is going to return an iffy, which is just going to return or date, random date. Since this is not very necessary, you can go ahead with it with the same methods that we have created, but since it is necessary, so we need to do this. Okay, so it is enough, and now we can go ahead with the instantiation. So let's go create a WASM module method, and we are going to use the web API which is available for WebAssembly. So it is WebAssembly dot instantiate streaming, and we are going to actually, it takes a buffer of data. So fetch will give us an array buffer. So fetch, and fetch takes WASM module URL. This is what build.js URL we are taking in a params here. So this is WASM module URL, and second params that it takes is import object that we just created. Okay, so this is going to give us our WASM module, and we can just simply return WASM module. So looks good for now. And one more thing that we can use and we can do in WebAssembly script is that we can import our JavaScript methods. So like there is a JavaScript method called console.log. Okay, so you can use this console.log inside assembly script. So how can we do that? Suppose you want to import some JavaScript methods or some inbuilt JavaScript methods or your custom methods. So you can just inside your import object, you just create an index key, and index key you can just define your method inside your key. So suppose I'm going to take the parameter d, and I'm just going to console it. This is our simple method, and we want it to be imported. Okay, so this is we have created, and now we need to declare this. We need to declare this inside our assembly script file, since it is empty for now, but we need to declare this log method here. So it will be declare function, which is log and of d, and type will be of whatever type you want to give. Suppose we want to print a string, so you can give it a string here, and what type it will return that you need to define. For now, void. Okay, so now when you write your assembly script methods, you can use this long method here. So this is amazing, and that you can use here. Okay, so we have imported our script, and we have our WASM module here which we can use now. So now what we are going to do is, when the assembly script button is clicked inside the WASM module, we are going to create a function of main WASM. So this is where our main function execution start. Okay, so let's go ahead and create a main WASM method, function main WASM. Okay, So main WASM actually should have two values that we can pass. It should have a knowledge of width and height of canvas, since it is going to be used very frequently, and we are going to name this as an async function. Okay, so we have width and height here. Okay, so when this function will execute, we will have a WASM module, and inside WASM module we can access or export methods. Okay, but before jumping to export methods and before using this assembly script methods, first we need to understand how WebAssembly memory works, because if we deal with internal memory on our own, we can actually create a much faster program. So let's see how the memory of WebAssembly works and how can we deal with it. So I'm going to show you a simple memory program. So how can we use memory pointers to access the values? So this is our assembly script file index.ts. So first of all, let us allocate some memory. As we discussed earlier, in assembly script, memory grows in pages. So and every page consists of 64 kilobytes of memory. Okay, so here we have asked assembly script to allocate at least 64 kilobytes of memory. So now we can go ahead. So let's create a memory pointer. Okay, so it will be const memory ptr of i32 type for now, and give it a 0 index. Okay, so this is a memory pointer, and let's have a value. It is also of i32 type, and let it be 15. Okay, so these are two values. Okay, so we have to store this in our memory buffer. Okay, at this memory pointer. So to store it, we can use store. To store takes of u it is an unsigned 8-bit type. So index means memory pointer, at which memory you want to store the value and what value you want to store it. Okay, this is what it looks like. So you store a value in memory pointer like this. Now let's create a simple function to access this memory. So suppose get data, simple function it is. It will return of i32 type, and to access a memory, what you can do is you can load unsigned data type. It is also an inbuilt method of assembly script that you can use, and which memory you want to access. So it is memory pointer. So we want the data which is kept at this memory pointer. Actually I misspelled it. Yeah, so this is memory pointer, and it is going to return it, and we can use this. So now if we go to index.js, and now let us use WASM module, which is our imported module, instantiated module. So it actually WASM module dot instance dot exports. So it is going to give us all the exports. So there will be a memory export by default, and then there will be a get data. This we have exported by default. Okay, so we can use this method. So one thing that we can learn here is, now you have allocated some point memory and you have stored some variables in WASM memory buffer. Now if you want to access that memory buffer from your JavaScript, how can you do that? So you can see there is a WASM memory buffer attached like this, and JavaScript can access all the memory buffers according to its needs. Okay, so let us create temp memory buffer, temp data, and it will be of unsigned 8 int type, unsigned 8 array, and memory dot buffer. So this is memory that we have exported actually. So it's memory buffer. Now this array will consist of all the values in the memory that are present for assembly script. Okay, so let's go ahead and console.log it. So if we console.log temp data 0, okay, so as we see that in time at 0 pointer we have stored 15, so it should console.log 15. Okay, so we are going to use the same program, and let's go and run it. So let's go ahead and create our build and create our WASM file, npm run as build. So this is going to generate release.wasm file. So it is generated. Now we can run the server npsxr, and looks good. Only one difference is there, that we need to make a change here, that we are actually importing a WASM file and we have given the path for JavaScript. So let's go ahead and run it now. Okay, so let's go to console and run it. So you can see we are getting 15 value. So at index 0, as you see, we stored 15, and from JavaScript we are trying to console.log the memory buffer, and we are able to access the memory from our JavaScript. So let us now go and create the same method that we created in JavaScript. So let's remove this get data method, as we have understood this. Let's keep the memory pointer, as we will be needing it in further explanations. So we are going to export the memory, and we are going to export the memory pointer. Okay, so we need to give width and height again to the canvas. So let me close this so that you can see. Yeah, so since we are doing it for the both WASM and JavaScript, so why not take it out and make it a common. Okay, this is done. Now if we go to WASM, so we need, what we did in JavaScript, we first generated a random image. Okay, so we need to create a random image method for assembly script also. Okay, so let's go ahead and create it. So let us name it as export function generate random. Okay, so it will take width of I32 type and height. Only difference will come, logic will be same like what we did in generate random method. Here we created an image data and we filled with the random values. So this is what we are going to do here, only we are going to do it with the rules of assembly script. So it is going to return null, a void. So let us loop over it now. Let y equal to 0. Okay, so we are going to loop over every pixel and generate random values. So let us now access the pixel index. So we are going to save our first pixel value at memory PTR. Okay, and then second, then if I give you an example, first pixel will be at 0, and 0 will actually store the value of r of the first pixel. Then 1 will store g, b, and so it will be r, g, b, and a. 3 will be storing the 4 alpha actually. Then 4, 5, 6, 7, 8. So this is for one pixel, this is for second pixel. This is how a memory buffer of assembly script will look like. Similarly, it is, you can consider it as an array. So let's go ahead and build it. So memory pointer is our first index, as you can consider this. So memory pointer plus, then it will be y into width plus x into 4. Okay, so this is going to give us the actual index. Since memory pointer is 0 for now, so it won't make any difference. But why we are doing this, because if sometimes your memory, you can actually give a memory base in your assembly script, and when you give a memory base, you tell your assembly script that you want to allocate some byte of memory for different usage. So at that in that case, your memory pointer will not start from 0, it will start from 100 or 200, whatever memory base you are giving according to that. Okay, so at that time then the difference will come. But for now, to consider so that we can maintain with the same logic, we are going to do this. Okay, so now we have to store the values. So as we know, to store a value at a pointer in assembly script, we can do this pixel index, and what value we want to store. Since we are generating a random value from 0 to 255, so let us, it will be typecasted to unsigned 8 type, since it is of unsigned 8 type. So let us generate a random value, and it will be multiplied by 256. Okay, so this will be for red, so it will store the red color value. Okay, similarly we have to do for green and blue. Green, and this will be for blue. So, and another will be for alpha, as we know, and as we did hard coding in our case of JavaScript also, we are going to do the same, since we want the opacity to be maximum. Okay, and one thing we missed, that we need to increase the index here of our memory pointer. Okay, so at every type we are storing 8 type, we are storing the 8-bit integer. Okay, so this looks good, and we have actually stored the random values now, you know. And let me remove this. So we have written our generate random method here. So now we can actually, since we have exported it, we can use it here. So let's use it, and we need to create the build also, so that it is available for export. Let us create a build. So the build is created. So like we did earlier, we need to access the memory buffer of our WASM memory in our JavaScript file. So let us call this as WASM byte memory, and it will be as called new unsigned 8 array, and as we know, it will be memory.buffer. Now we know that this WASM byte memory, by using the index, we can actually fetch the value of all the values that we have stored in our WASM memory buffer. Okay, so now let us create a random image now. So to create a random image, we can do const and image equal to new image data, like we did earlier, and we have to give width and height, that width and height of image data that we want to generate, since we have taken the width and height from there. So it will generate a random it will generate a random image data. Now as we know that random image, what we did earlier in JavaScript, we created a random image. If we go to generate random function, we generate a new image data, and inside that random image dot data, we set all the pixel values. So this is what we need to do for WASM also. Okay, so to do that, what we can do is random image dot data dot set. So before doing this, one thing also we can do is we can run this method and create a random values now in the memory. So let us run this and pass width and height. Okay, so generate random is going to fill our memory with random RGBA values, okay, which we can access using this WASM byte memory array. Okay, so when we now all the values are inside, WASM has stored all the values in its memory buffer. Now we need to copy that buffer and all the buffer values inside this data array. So how can we do that? So while we set, we can use WASM byte memory dot, since memory buffer can be of larger size, okay, so we need to slice out the values that is required for us. Okay, so since we have exported the memory pointer also, let us export it, since we will be needing it to slice the memory ptr. So this is memory pointer which is exported. Now to slice it, we are going to, whenever we export a variable, we cannot console.log directly. We have to actually print a memory point. Like if we have exported this variable, to access its value, we need to do memory pointer dot value or dot value of method. So like we can do memory ptr dot value of, so it will print 0 since it is 0 for now, no? Constant. And slice, this is memory pointer value of, then another memory would be, next index would be memory pointer plus, since there are total there, sorry, so we are generating an image of width and height. Okay, so as we discussed earlier, to generate, now we are slicing all the pixels that are stored in our WASM byte memory. So what we can do is we can just add and multiply width and height multiply by 4. So this is going to generate all the last index in the memory buffer after storing all the pixel values including RGBA. Okay, so this is going to slice out our memory values and going to set it inside a data pixel. Okay, looks good for now. Let us now override our canvas context and override with our random image data. So ctx dot put image data, and this is our image data, random image, and it will return from 0, 0 xy. Okay, so this is written. So now if we run the server, let's run the build now. Okay, let's generate and sort. So nothing came up, and let's see why. So we are getting an error that memory access out of bounds. So this is something I wanted you to see, memory access is out of bounds. So why is it happening? Because we have allocated only 64 kilobytes of memory, right? And what we are doing here is we have generated a image. We are trying to generate an image of width and height 500 cross 500. Okay, so we know the logic that if we are generating an image of 500 500 into 500, then how many what will be the array length of pixels? So that will be multiplied by 4. Okay, so this is the array length that will be there, so it will be 10 to the power 6, right? So this is the array length. Array length means RGBA, for all the pixel values. Okay, so it will, and every pixel value, as we discussed, it was around 8-bit. It was 8-bit. So how much memory it is going to store? So it will be 8 into 10 to the power 6 bits, right? So this amount of memory we need at least to make it work. So to play on the safer side, let us now, I'm setting it to 16. So it will allocate a memory of 16 into 64 kilobytes. Okay, 16 into 64 kilobytes of memory, which I think it will be enough for our use case. So since we have changed the memory, let us now create the build again. And let us now run the server. Now if we run it and let us console log generate and sort. W is not defined. Let us go and see what is the issue on line number 20. Yeah, actually it is width and height. So it will be width into height So let us go. So see, now we are generating a random image in WebAssembly. This is cool. And now what we have to do is we have to just sort these pixels, and we are going to develop a clone methods that we developed in JavaScript. That is what we are going to write just for WebAssembly. So let us do that. So let us go to our assembly script, and we are going to write a sort function here. So it will be export function, and let's name it sort new. Okay, and it also accepts a width and height. Okay, and it will also return void, since all the changes will be inside the memory pointer, and memory pointer you can access direct JavaScript, so no need to return anything. So what we did in JavaScript, let's have a small look. So this is a sorting method, and we actually created our bubble sort method. We created a brightness method and a soft pixel method. Okay, so let us do that. So we will be needing a brightness method also. So let's create a brightness method. So brightness method will take x as i32, y as i32 type, and width as i32 type. Okay, and it is going to return f32. Why f32 type? Because if we go to a JavaScript method, you see we are trying to generate a float here. Okay, so let us do that now. So first we need to generate a pixel index, and since we know, we use memory pointer plus y into width plus x into 4, and this is going to give us a memory pointer. Now just we have to return the total intensity, luminous intensity. So we need to load the value from our, like what we tried to in our JavaScript we used array and access the value through big index, but in assembly script we will using memory pointer index, and since load and store are the methods that we use to access and write to the memory in assembly script, so let us do that. So it will be pixel index, so it will give our value. Then for G we use 0.715. So this will be for G. Then let's write for B 0.0722. So we have written this, and this is going to give us our pixel index. Okay, luminous intensity, sorry. So now we can use this method. And one more method that was built in JavaScript, that was swap pixels. In swap pixels, what we did was we just swapped all our RGB pixels. So let us write a swap pixel value method. Okay, so what swap pixel will take as an argument? It will be x, y, and width. X will be i32, y will be i32, and width will be of i32. It is going to return void, since it is going to make the change in the memory, and we have access to the memory everywhere. Now we will generate 2 pixel index like we did here. Okay, so actually we can copy this also. We can copy this here, and only thing we need to do is add memory pointer to it. Okay, So 2 pixel index have been generated here. Okay, so now we will loop through that I equal to 0, I less 3. Since we are taking change for 0 1 2 means RGB and alpha will be constant. So let us access the temp. So load unsigned date type, and we are going to access the index of what we accessed here. We access pixel index 1 plus, so it will be pixel index 1 plus I. Okay, so we have loaded the memory. Now we need to store it. So where we want to store? We want to store it at pixel index I, same I1 plus I. Okay, I1 plus I. And what we store what we get from I2, pixel index I2. So it will be pixel index I2 plus I. Okay, and then again we are going to store into it. So it will be pixel index I2 plus I, and temp that we stored we are going to write here, and then we are going to write our alpha values here. Since it is not required, but we are doing for JavaScript, so let us do it for here also. Pixel index plus 3, which will store to 55. Let's copy that only, and p plus 2. So a sweet method of swap pixels we have written in assembly script, and it looks good for now. And we have swapped the pixels. Let us now use our sorting method. So let us pixel. So we will copy. We'll check from JavaScript methods. So we do not make any other calls or any unnecessary calls, because we want to be very sure that we are doing the exact same thing in WASM and JavaScript, because then we will be able to compare it on a equal level. So pixel intensity A, and it is going to get the brightness. So brightness will take three values actually, x, y, and width. Okay, and similarly for pixel intensity 2, actually B, and it will be this x plus 1, and we need to apply the condition here same as we did. So x plus 1 should not exceed width. If it is exceeding, then we need to return 0 or null anything, just to fail the case. So if pixel intensity A exists and pixel intensity B exists, and pixel intensity A is less than pixel intensity B, so then we are going for swapping. Okay, so let's go ahead and call our swap pixels method. So it will take x, y, and width. Okay, and one thing that we are missing, did changes. We need to track the changes. Until the change is happening, we need to keep running our bubble sort method. So we'll consider no changes happening. Let us add a do while loop, and while there's change, we will keep running our sorting algorithm, and whenever there is change, we set it to true. Yes, it means this pixel needs to be sorted, and here we will set it to false. Okay, so looks good. We have written a sort new algorithm here, and as you can see, the same methods we wrote in JavaScript we have written in assembly script also. Okay, so let us import this in our JavaScript code here. So sort new is the only method that we want. So we have exported our sort new method that we wrote in our assembly script. So let us use this now. We have generated our random image here. Okay, using assembly script method only. Now what we are going to do is we are going to run our sort new method, so that we can make the changes to our WASM buffer. So since when we generated the random image, we override the memory buffer, and when we run the sort new, what we are doing is we are making the changes to memory pointers only, to the same memory pointers. Okay, so we don't need to pass any array or anything like that. So let us give it width and height, since sort new accepts only two parameters, width and height. Okay, so what it will, when this method will run, it is going to sort all our pixels according to their intensity. Now we need to again slice of memory. So let us some image data array, let's name it this, and some byte memory dot slice. Okay, so similarly what we are going to do, memory pointer dot value of, and again memory pointer plus width into height into 4. Okay, and this will be value of. So this is going to slice out the memory. Okay, so now let us use this. We could have also, when we sliced it, we could have saved it in one array and used it, but no issues, we can do it later. So we have all the sort, so consider this array as a sorted array now. So now if we go ahead and set this data to our image data. So let us create our image data first. So it will be sort image data, and sort ctx is sort underscore ctx. It is the canvas context for sort canvas, and create image data. So this is going to create our image data and width and height that it accepts. Okay, now once you have this sort image data, so create image data, now we can set the data to this variable. So sort image data dot set. So dot set and some memory data array. Okay, this is what we generated. Now we have set the image data. So let us now create sort ctx dot, and we are going to put this image data to our image context, and 0, 0. Okay, so this is the sort context, and when we created an image data, it is similar to this. There is nothing to be confused about. So you could have used new image data also. So when we created an image data similar what we did here, and we are just doing data.set, we are writing all the values. Okay, so we are writing all the values, and now once we are written, we are drawing it. It is just like drawing on a canvas. So it is written now. Now let us see if it works. Let us create the build if we exported some new methods. Now let us run the server. Let us see if it works. Amazing, and it looks great, no errors, and as you can see, we have sorted it. Now only thing left is time taken. We need to store the time taken, right? So let us see how can we do that. So if we scroll down, this is the button event listener where we start listening to the click event, and this is where execution starts. So let us attach our time taken method here. So I'm going to store let x1 equal to performance.now. Since performance.now is much more accurate, so we'll start calculating the time from here, and since when else is completed, it will be x2 equal to performance.now. Okay, So whatever method runs, either it is WASM or JavaScript, time will be calculated for that. Okay, now we are just going to override inside the inner HTML. So what is the inner HTML for that? As you see, time taken is id is time underscore taken, right? So time underscore taken dot inner HTML equal to. So let us create this string time taken. It will be, let's name it x2 minus x1, and since it is going to be large number of decimals, so let's keep it to fixed 2 by decimal values. So only 2 decimal values will be printed. Okay, so looks good for now. Now let us run again. Okay, let me clear it. First let us run for JavaScript. Yeah, we can see the time again. So yeah, JavaScript, we can see the time. Now change to WASM. Let us see, drastic difference, almost half. WASM is running almost half, so looks good. So we have built our demo project and we saw that WASM is much better than JavaScript when it comes to computation power. So now you can go ahead and build your demo and personal projects in WASM and make use of WASM's power. And some of the tools that I would recommend to the beginners, that you can use WASM by example dev site. Personally, I found this website really helpful. So you can take a look at it. And another site that I would recommend is AssemblyScript book. The documentation of AssemblyScript is really amazing and it will get you started in no time. So you should check this out. So the pixel sorting algorithm that we have built, I am going to push it to this our GitHub repo, and you can check this code, clone it, and make it your own. Make the changes, right? So if I missed something, then let me know in the comments below. And if you like to add anything, then also write it down in the comments, and I will check it out. And thank you for watching this video, and I will meet you in the next one.